Hello everyone, this is lecture 5 of course PE 645. In today's lecture we are going to deal with a new second order feature technique is called gray level size zone matrix, or in short GLSZM. This technique is sophisticated and valuable that can be applied in image processing, especially in medical image analysis, because this technique is used to extract detailed and quantitative information about the texture and structure of the image. And it provides a robust way to quantify the texture of tissues in radiographic images, which can be crucial for diagnosing and characterizing various medical conditions. The core concept of GLSZM is to represent the size distribution of connected regions or zones that share the same gray level or intensity within an image. A region or a zone is defined as a group of contiguous pixels that all have the same intensity value or gray level value. These zones or regions in two dimensions are connected either through four connectivity, where we are connecting the adjacent horizontal and vertical direction from left and right, top and bottom, or eight connectivity, where we include also the diagonals, top left, top right, bottom right, and the size zone matrix captures this information in a matrix where each element in that matrix represents the number of zones or regions of a particular size for each specific gray level. So we can say for the intensity or gray level 5, we have a region that connects 5 pixels or 7 pixels as an example. The size zone matrix requires also 3 parameters: the number of gray levels, which is represented by n, similar to GLRLM. We also require the parameter n, and this parameter indicates the number of discrete intensity levels present in the image. The maximum zone size, or represented by z, this parameter refers to the maximum number of zone sizes required to build the matrix. Theoretically, z is determined and calculated as the image shape multiplication. In other words, we are multiplying width by the height for 2D matrices and width by height by depth for 3D matrices. The third parameter is the connectivity C. As we mentioned, we have two options for connectivity and eight connectivity, and this happens for 2D matrices, and we will see how this number will change for 3D matrices to become 6 for horizontal, vertical, and z-axis, and 26 for all directions. So now we have 3 parameters, n, z, and c. So now we need to build a matrix M, which represents the size zone matrix, and we need to define the 3 parameters initially based on the given matrix. So n in this case will be 4 because we have 4 unique values, or the maximum number is 3. So we add 1 to that number to become 4. And C, we determine if we need to consider the diagonal axis and the connections or not. If so, we select 8, and if not, we select 4 for only horizontal and vertical connections. And Z will equal to 10, and let's assume that number, and we will understand after a bit why we assume that number and what is the best practice to select the Z value, and why not we didn't multiply the width by the height and build the initial size zone matrix based on it. After that, we will create an empty matrix with the shape of n multiplied by z, so the shape will be 4 multiplied by 10. 4 represents the gray levels, and we set for each row a gray level, for example, gray level 0, 1, 2, and 3. And for the columns, we set the zones. We have 10 zones, so we are setting the first column is zone 1 and the last is zone 10, and assume that there is a number here with a value of 1 at gray level 1 and zone 4. What does it mean? This means that there are 4 connected pixels with the value of gray level 1, and this happens once in the matrix. So how do we set these numbers? We have a matrix, we build the size zone matrix, and we need to start from the top left corner and move to each pixel which is not seen. If the pixel is visited, so we ignore it. So let's start. For the first pixel, we will need to find the 8 connections around it, which is left, right, top, and bottom, and the diagonals. And we need to check for each of the 8 connections if any of them or multiple of them are the same value, similar to the current pixel or not. So the one here is similar to here and both of them are in the connections. So the count will be 2. And we need to check further if the new one is connected to any regions or not. We will find that there is no value here is similar to 1. So the connected region or zone will be 2. So we set at gray level 1 and zone 2, which represents the number of connected pixels with the same value. We set a value of 1 or increment the field from 0 to 1. After that, we will move to the next pixel, which is 2. We will find also the surrounding with the 8 connectivity because we set C to 8. We will find that 1. And if we are here, we find another pixel here, another here, and a third here. We will do the same for each of them. We will check here. We see no surrounding pixel other than the visited one, so we ignore that. We go here, so we find the pixel. We go here, we find the pixel, and I am currently counting only the not visited pixels. We stop here, we will find the pixel. We stop here, there are no pixels. We stop here, there is a pixel. We stop here, there are no surrounding pixel with the same value of 2. So there are no more 2 pixels. So the count will be 9. So we go to the gray level of 2 and the zone of 9 and increment the field. We do the same for the next pixel. There is only one region, so we go to gray level 1 and zone of 1 and increment the field by 1. After that, we will go to the pixel. We will find that it's visited, so we will skip it. Next, we will move to the next pixel. We will find the region is here, so we will increment the field of 1 and zone of 3 by 1. We can move to 0, it's a zone of 1, next to 3, a zone of 2, then 0, a zone of 1. So that field was 1 and we incremented it, it will become 2. After that, we go to the next pixel. It's 1 connected to here, connected to here, connected to here. So we have 4 ones. So we go to gray level of 1 and zone of 4 and increment that field. We will do the same for the rest of the image. There is 1 only here and 1 only here. So we incremented the gray level 0 and 3 at zone size 1 by 1. So it will become 3 instead of 2 and 2 instead of 1. So what we did with each region or each pixel which is not visited, that we are checking all of the surrounding because we are setting C by 8. But if we were setting C by 4, then we will stop by a pixel and check only the horizontal and vertical axis. So how to do that programmatically? As we mentioned, we are looping on each pixel, and if we are stopping by the 2, we are checking all of the connections in the 8 directions. So we need to find the neighbor pixel and the current pixel share the same intensity value. So when we select the next pixel or the neighbor, it should be the same value, which is 2 here, as we did in the example. Before doing that, we need to check the boundaries. Why? Because we are here, so we have 4 connections that are outside the boundary. So if we try to access the matrix at a value of -1 or -2, it will be a wrong value and it may raise an error. So we need to check that each pixel here or each neighbor is inside the left and right, top and bottom, and if so, we continue the check that the neighbor and the current pixel share the same value. The third constraint that we did, we need to ensure that each pixel, which is the neighbor in that case, that we are going to visit is not seen. So this can be solved as we did with the GLRLM matrix with the scene matrix, that we need to flag each visited pixel by a true value or one value in the scene matrix, so we will go to the pixel again and see that this pixel is visited, so we can skip it and ignore. As you see, when we stopped here in the example, we found that there are 3 neighbors that share the same value, which is 2. If you imagine that we have a pixel of value of 2, which is split in 3 portions, each also 3 branches, each can also be split, because if we are here, for example, it will split also into 2 branches. So we are building now something like a tree. And to solve that programmatically with an easy way, we use recursion. Recursion in that case will handle the branching, and the meaning of recursion in programming is that you have a function that calls itself. So if we have a function called x, so we are calling the function again x, but with new parameters. And this function will call itself again and again and again. But if we kept it like that, it will go to infinity. So at a certain condition or a certain level, we stop the recursion. So we have a function that calls itself and so on until as said at a certain level that we need to stop the recursion. After that, each called function will move backward and return some values to its parent. So this function will return some values here and return some values here and return some values here. And why we are doing that? Because each individual branch is doing the same. This one will do the same with that one and that one, which means each of them checks the 8 neighbors. So we can let the first 2 is here, which represents that one, and for each neighbor we will call the function or we will do recursion based on it. So the first 2 will call or perform recursion 3 times, each one is 2, and that 2 will also perform a recursion, and that 2 will perform a recursion until we reach a specific condition that then returns a value to the parent. For example, here this function will say that we found 2 neighbors, so 2 plus 1, this function will say that we found 3 neighbors, and so on. And we will also illustrate the recursion when we go to the code. After that, we need to build the connected regions together, so we can count the number of each region corresponding to each intensity value. And this can be done by building a dictionary of pixels, where the key is the gray level and the values are initially set to an empty list. And by performing recursion and looping on each pixel, we will first check the constraints and conditions that we illustrated here, which are the boundaries, they are the same values and not revisited. And once we discover and find a neighbor pixel that satisfies these constraints, we add the location of that pixel to the dictionary. So for example, the value of 1 says that the pixel at 0 and 0 is connected to 1 and 1, which here I mean the coordinates or the indices. So we added in the list a tuple with these 2 values. And here 0 and 4 is connected to 1 and 3 is connected to 2 and 4, which is another one here. And here 3 and 0 is connected to 3 and 1, 3 and 2, 4 and 3, which is also here. So we now have, for the gray level one, we have 3 elements in the list. Each represents the coordinates of the connected pixels. By building that dictionary, we now can build the size zone matrix. How can we do that? We first count the maximum length of the connected regions. In other words, we check each element in the list and check its length and tries to find the maximum of these lengths. So here we have the value of 0 with 3 elements, where each is 1 in a length. And here 2, here 3 pixels in a region, here 4, here 1, here 2, here 1, and for the gray level 2 we have 9. Why do we do that? Because once we get the maximum number, we will create the size zone matrix and define the z-value. As I mentioned from a bit, that we assumed the value of 10 to z, as we did here, and we mentioned theoretically that we need to multiply the shape, which is theoretically the maximum zone level that can be reached. Imagine if the matrix is all with the same value, so the maximum length will be the width multiplied by the height. But to avoid any excessive large matrix with zeros, we can practically check the maximum length and define the z-value based on it. Because if we build any zones after that, its value will be 0. So based on the lengths here, we are filling the table. So at level 0, we have 3 ones, so we set here 3. At level 1, we have 2, 3, and 4, so we go to zone 2 and 3 and 4 and fill it by 1 or increment the field. The same for gray level 2, we have a single zone level of 9, we increment that field. And for gray level 3, we have 2 zones with 1, so here is 2, and a single zone with 2, so we fill here by 1. By doing that, now we have the size zone matrix. So how to do that programmatically? This function will be responsible for returning the size zone dictionary. So as we saw in the discussion, in the lecture, we have some constraints that need to be applied, and we have recursion that we need to apply to get all of the connected regions, and we need to use that and fill a dictionary. So simply, we created a helper function here, which will be responsible on the recursion. And if you see, we defined a function inside a function, and this is normal in Python. This function will take the index of I and j of the current pixel, and the current pixel, and a region list, which is initially set to be empty list, that need to be filled with indices, and based on the final list, we can take that list and include it in our dictionary. It also will get the seam matrix, which will be in the same shape of the original matrix, and initially set to 0 or false, and the type of connectivity, which is default by 4. And this is an optional parameter that can be redefined to 8 when we are calling it. Internally inside the function, we first checked the boundaries, left, right to bottom, and checked that the value of the current pixel is similar to the value of the neighbor pixel. And also we checked that is the neighbor is set before in our region or not. So we do that to avoid any duplication. So we cannot say that 0 and 0 is connected to 0 and 0. It cannot connect to itself. So if any of these conditions is satisfied, it will return without continuing the recursion or the process. If both are not the same, if the neighbor is found, or we are outside the boundaries. If all of these conditions are satisfied, we add the neighbor to our region, and we set the corresponding value in the seam matrix to be 1, so it cannot be revisited again. And we need to spread and perform another recursion for all of the neighbors. So we are getting the neighbors in left and right, top and bottom, by simply passing the same parameters which are here, and only changing the I and j values. Here, simply are moving left and right, top and bottom. And if the connection is defined here by 8, so we will need also to include the diagonals. So if the connection is 8, we will include the diagonals. Top left, top right, bottom left, bottom right. So this is the rule of helper function. Check constraints, change the flag of the seam matrix, add the neighbor to the region, perform another branching or recursion. So let's collapse that function. So where do we use and call that helper function? As we mentioned during our solution in the example, we said we need to loop on each pixel. So here we are looping on each pixel. If the pixel is seen, continue and ignore it. Get the current pixel, and if the current pixel value is not in the regions, which is the dictionary or the size zone dictionary, and which is initially set to an empty dictionary, create an empty list in that dictionary that reflects the current pixel value, which is here. The dictionary is initially set to 0. So if the 0 is not found in the keys, we will set it with an empty list. So how to get these values? This is done by calling the function which we illustrated from a bit. And as mentioned, the region is initially set to an empty set or list or a tuple, which is defined here. This recursion will be performed twice, 3 times, 4 times, until the conditions we mentioned here, any of them is satisfied. So it will return from its recursion and return back. So what is going to return? If you see here, we are passing the region and scene matrix, which is also passed here and passed here and in all calls. And internally, we are modifying them. So once the recursion is completed and this function is finished from its execution from the current pixel and found all of the neighbors, in the memory, these two variables will be modified. Why? Because in the memory, we are dealing by reference with the objects. So if a function that we are calling defined a value, it will reflect in our original matrix. So we created the C matrix here and the region here and passed them to the function. That function modifies the value of each of them. So once we reach that line, the region and the C matrix are updated. After that, if the length of the region is still empty, ignore, and if not, which is greater than 0, append that region to the corresponding current pixel in the dictionary. By doing that on each of the pixels, we now got the size zone dictionary. So let's collapse that function and call that function and give it a matrix which is defined to the same matrix in our example, and convert it to a numpy array and pass the connectivity of 4. So after it completes its recursion process, it will get the size zone dictionary. After that, we need to define the size zone matrix. The n will be the maximum number defined here plus 1, and z will be the maximum length of the regions. So we define the maximum function. We looped on each pixel and looped on each zone inside the zones in each pixel and got the length. And this approach is called comprehensive lists, which is a bit faster than using traditional for loops. So it will get a list with all of the lengths as we did here, 1, 1, 1, 2, 3, 4, 1, 2, 1, and we need to find the maximum number, which will be here 9. So z in that case will be 9. We define the empty matrix, the size zone 1, and start to fill the dictionary with the count. We are setting the pixel and len zone minus 1, because if you notice here we start by 1 and in C's in Python starts by 0. So we subtract here 1 and increment that field by 1. After that, we print the matrix, the size zone dictionary, and the size zone matrix. Once the code is executed, we will get the matrix, the size zone dictionary, and the size zone matrix. And you can confirm the numbers in the results with the numbers in our solution. And the same for the dictionary, you can confirm the dictionary with that one. And that output will be obtained when we set that value to 8 to be similar to our solution. but if we set it to 4, it will get a different value. This is another example. There is a matrix. We executed it using 8 and using 4, and as you see here, the size zone matrices are not the same. Once we got the size zone matrix, a range of statistical measures can be derived from that matrix. These features will provide insights into the texture and structure of the corresponding image. There are many size zone features, where many of them will be the same with the gray level run length matrix, but instead of using the run lengths, we are using the size, and this is the difference between both of them. The approach of calculation of the matrix that we are going to calculate the features from it. So as we go, you will find that most of these formulas are the same with the run lengths, but on a different matrix. There are small zone and large zone in phases that measure the distribution of small and large size respectively, and higher values of the small zone will indicate more small size zones, and higher values for large zone will indicate more large size zones. The gray level non-uniformity, it will measure the variability of gray levels, and lower values will indicate more uniform gray levels across the image. Zone size non-uniformity, this will measure the same, but instead of the gray level, it will reflect the zone sizes. Zone percentage, it will measure the ratio between the number of zones to the number of pixels, and these are the corresponding formulas. And if you notice also, P here is the normalized version of the size zone matrix. There is gray level variance. It will measure the variance in gray levels, and it will indicate the spread of gray level values. Zone size variance, it's similar but on the zone sizes. Zone size entropy, it will measure the randomness in the distribution of zone sizes, and higher values of zone size entropy indicate more complexity of the image, and the epsilon value here is a small number to avoid any values that are zeros, so there is no log of 0. Low gray level zone in phases and high gray level zone in phases, they measure the distribution of low gray and high gray level zone respectively, and higher values of the low gray level will indicate more low gray level zones, and higher values of high gray level zone will indicate more high gray level zones. So for the small zone and large zone here, we are dividing by and multiplying by j square, and here we are dividing and multiplying by I square. For the small zone, low gray level, and the other combination, we are combining both the gray level and zone sizes. Here we divide by I and j squared. Here we multiply by I and j squared, and once we divide, we are getting low or smaller values. That's why we mentioned small and low. And for I and j in the multiplication, large and high. The other combinations, you multiply by I square and divide by j square. So the I will reflect the high gray level and j will reflect the small zone. This is because the I reflects the counter of the gray levels and j reflects the counter of size zones. And the same here, j is multiplied, so we have large zone, and I is divided, so we have low gray level. And all of them will measure the distribution. So let's calculate, for example, the small zone in phases. We will first need to calculate n, and n here is the count of all of these values in the zone matrix. So we will count and sum all of these. It will be equal to 10. Then we will loop on each element, which practically will be the normalized version. But for simplicity here, we will keep the pixel as it is. So 3 is divided by 1 square, 2 is divided by 1 square, 1 is divided by 2 square, 1 is divided by 2 square, 1 is divided by 3 square, 1 is divided by 4 square, 1 is divided by 9 square. Sum all of that and divide by 10, we will get a value approximately 0.57. And for The large zone in phases, we will do the same, but instead of division, we convert it to multiplication. So for example, 1 is multiplied by 9 square, 2 multiplied by 1 square, 1 multiplied by 4 square. We will do all of the summation and divide by 10. It will become 11.9. And for the small zone high gray level in phases, you will multiply by the square of the gray level and divide by the square of the zone level. And notice that the counters start from 1. So when we multiply by the value of gray levels, we start the count of 1. So 3 will be multiplied by 1 square and divided by 1 square. 1 will be multiplied by 2 square and divided by 2 square. 2 will be multiplied by 4 square and divided by 1 square. 1 will be multiplied by 4 square and divided by 2 square, and the same until we reach that 1. 1 will be multiplied by 3 square and divided by 9 square, and by doing all of the calculation and dividing by 10, we will get an approximate value of that feature of 4.08. To do that using code, we have used the same functions that we illustrated and created another function that encapsulate the calculation of the dictionary N and Z and filling the size zone matrix, and then returns all of that to be used for further processing. After defining the matrix, we called only that matrix, which internally called the find connected regions function, and this function will return the size zone matrix and dictionary N and Z because we will need them in our calculations. And we defined a connectivity of 8 to be similar to our solution, and calculated the n value in the formulas, which we will write here size zone n, which will be the sum of the size zone matrix. After that, similar to what we illustrated in the previous lecture on calculating the GLRLM features, we did the same here for each feature. For example, here, the small zone low gray level, we need to divide by I square and J square. The I is mentioned, as mentioned, reflects the gray level, and J reflects the size zone. So this is the square of I and this is the square of J, and we are adding a very small epsilon value here to avoid any division by 0, because here we are performing division and one of them may become 0. For example, the large zone low gray level in phases, we are multiplying by the square of J square because there is large here, and dividing by I square, which is low gray level here. And you can also add the epsilon value to avoid also any division by 0. After performing all of these features calculations, we are printing them. So for example, the small zone high gray is 4.08, and this is our print of results. You can confirm that they are the same number. And for our large zone in phases, it's 11.9, which is here. You can do the same for other features to confirm that your calculations are correct. After that, we need to apply the size zone matrix and features on a 2D image, then a 3D image. In that code, we have used the same two functions and encapsulated all of the features in a function that calculates the different features that we mentioned and returns the dictionary of all of these features. And it's worth noting that we updated the function to include the epsilon value on each division to avoid any division by 0 or log of 0, as we mentioned here. So if we have an image, we can call that function, pass to it the size zone matrix, and it will calculate the features for us. So we have the image and the segmentation, as we do every time, loaded them, extracted the ROI and decoded based on the bounding rectangle. We called the size zone matrix function and then the size zone features, and for each feature we printed it, and we defined to normalize and ignore zeros. To perform normalization, we are dividing by the summation of the size zone matrix, and we are adding epsilon to avoid any division by 0. And to ignore the zeros, we added inside the loop of each zone in the function of calculating the size zone matrix that if you encountered that the current pixel is 0 and the flag is set to true, continue and ignore from the incrementing. When we execute the code, we will find this corresponding result. And if you notice here, these two numbers, that we have large zone with high gray level in our matrix because that number is very high, and we have few or less large zone low gray level in our matrix because this value is very low. The same is reflected here. Small zone, high gray level, we have a high value, and for the small zone, low gray level, we have a very small value. And this can indicate that the high gray level in our image is spread in our image, because as you see, we are getting the ROI and ignoring the zeros. So the calculations that will be performed on the zeros will be ignored. So for the low gray levels, its value will become very small, and this region has a higher value or higher gray level, which is reflected in that value and that value. You can also change between 4 connections and 8 connections. In our example, we used 4 connections, and here 8 connections. The value is incremented from 17K to 20K, and here decremented from 13K to 12K, which also can reflect that some of the small zones went to be large zones. We need also to apply that on a 3D volume. So we will do the same process, read the volumes, group the images, pad them, and apply that to our new 3D functions. In 2D, as we mentioned, we are using 8 and 4 connections, but for 3D, we have whether you are using 6 or 26 connections. So to represent it graphically, we have 3D volume to get the 6 connections, 1, 2, 3, 4, and 5 and 6 in the z-axis. And the 26 comes from all of the other connections. This to here, 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 until we reach here and here. So simply, instead of counting all of them, we have 9 pixels multiplied by 3 minus 1, which represents the current pixel. So it will be 27 minus 1 will be 26. If we did the same for 2D, 9 minus 1, it will be 8. As we mentioned, you need to group, apply padding, and then perform the functions. In the code, we have got the read volume functions that we were using in the previous codes, and here we added the 3D version. In it, we added another check on the z-axis. So now we have I, J, and K, and instead of using the image, we changed the keyword to, or the parameter to volume, and instead of accessing I and J, we are accessing now I, J, and K, and instead of any operations applied on I and J only, we are operating on I, J, and K. Here are the 6 operations or the recursion calls, and here are the rest of them to count all of them to 26. After that, we created 3 loops instead of 2 and did the same on I, J, and K. And for calculating the size zone matrix, we did the same to the version of 2D because we are getting a dictionary from the find connected 3D regions, which can be treated similar to the 2D version. And the same for the features, because the features are calculated on the size zone matrix, which will be in our case a 2D version. After that, we read a volume and the corresponding segmentation masks. We read it, defined the connectivity, and applied the function and printed the different features for the 3D volume. It's worth mentioning it's not necessary to include only 3 slices. You can add 4 or 5 or 2 or 6 or 7. It depends on the size of the volume in the original image or the complexity of the shape that you are going to include in your features. Once we execute the code, we will get these values for z equals to 6 and for z equals to 26. So in this lecture, we discussed the meaning of gray level size zone matrix, how to calculate the matrix and the corresponding features, understood an easy way, which is the recursion to calculate the size zone matrix or dictionary that will be converted later to a matrix. Then we applied that approach on an example, then a 2D image, and finally on a 3D volume.